NASA has confirmed that interstellar object ThreeI Atlast is not natural at all, but made of industrial material. NASA says it's only the third object to enter the solar system.
NASA has released stunning new images tonight showing a rare interstellar comet soaring through our solar system.
Now take a look. NASA unveiling close-up pictures earlier today of ThreeI Atlast.
ThreeI Atlast.
ThreeI Atlast.
ThreeI Atlast.
On November 24th, NASA officially released the comprehensive dataset from 15 spacecraft on the interstellar object ThreeI Atlast. ThreeI Atlast appears as a mysterious guest that forces a network of 15 probes and telescopes to surround it with observations from its symmetrical teardrop shape, gigantic hydrogen halo, rhythmic non-gravitational acceleration, dark shell resembling stealth material radar echoes, like a segmented surface, all the way to a trajectory that seems almost chosen, and a neat departure like a self-adjusting system. While Michio, Kaku and Avi Loeb use Atlast to put on the table the possibility of extraterrestrial technology, alongside extreme assessments, new findings point to K2-18b, with DMS traces suspected to be a biosignature salty water and lava tubes on Mars sprites in Earth's mesosphere, artificial stars created by lasers and meteorites thought to originate from Mercury. All of this weaves into a single tapestry where the universe continually sends half-hearted signals, not affirming anything definitively, but forcing us to keep two doors open at the same time. A universe that is only more complex than what current physics describes, or a universe where guests like ThreeI Atlast may have been created for a purpose that we still do not fully understand. In the next part, we will continue to trace the latest mysteries of ThreeI Atlast through the perspectives of Hubble James Webb and the candid assessments of leading scientists. When NASA quietly released the full gallery of images, spectra and trajectory logs for the interstellar visitor, ThreeI Atlast the atmosphere in mission room shifted. Screens that usually cycled through routine telemetry lingered on a single series of frames, and Atlast slowly resolved from scattered pixels into a coherent presence. Across the agency, teams noticed that 15 different spacecraft and observatories had been steered almost without precedent into positions where each could watch Atlast during the brief passage through the inner system. In the cautious language of mission planning, that level of attention is normally reserved for flagship targets, so Atlast seemed to have been promoted to a class apart. Some engineers called the campaign simple prudence, arguing that any interstellar body deserved every lens available, yet others asked why Atlast was being treated less like debris and more like a guest. Around conference tables, the official report stayed modest, but in the quiet moments afterward, another question took shape, asking what kind of history a fragment like Atlast might preserve from a distant birthplace. That line of reasoning did not require Atlast to be artificial or miraculous, only for humans to admit that looking away from such a messenger could be riskier than following Atlast with every tool they could spare. For theorists like Michio Kaku, accustomed to long stretches of incremental progress, the arrival of Atlast felt like a rare widening of the map, a chance to see how far known physics could be pushed. As plots and overlays from the 15 machines were stacked together, Atlast refused to sit comfortably inside old labels of comet or asteroid, and that unease quietly marked the visitor as potentially transformative. The first high-resolution frames from Hubble did not show a fuzzy, chaotic comet head. They showed a shape. Suspended against the star field, Atlast appeared as a soft, luminous teardrop, a smooth cocoon of light wrapped around a hidden core. Instead of ragged jets screaming off in random directions, the envelope around ThreeI Atlast looked almost even as if some quiet order held the dust in place. For astronomers used to asymmetry and turbulence, that calm outline was the first surprise Atlast offered. Most comets develop a bright nucleus and a fan of dust torn away by sunlight, yet the glow around Atlast seemed to hug the visitor like a fitted shell. Teams went back through catalogues comparing Atlast to past targets that Hubble had resolved with similar sharpness. The object refused easy company, sitting somewhere between known comet morphologies and a geometry that felt unnervingly deliberate, so analysts began to annotate Atlast with question marks in their notes. One camp proposed that Atlast might simply be young, with freshly exposed ice driving a dense uniform outflow. Another suggested that ThreeI Atlast could be rotating in just the right way to smear out irregularities into a single flowing contour. A smaller group wondered whether the envelope around Atlast functioned less like a random coma and more like a protective layer regulating how material escaped. No one in that group claimed engineering, yet the phrase controlled shell began to appear in the internal slides whenever Atlast was discussed late at night. For observers staring at the Hubble frames until their eyes blurred, the visitor felt strangely self-contained, as if Atlast were guarding whatever lay beneath the glow. That uneasy fascination pushed the community to look beyond visible light, and the next instruments aimed at Atlast would start to peel back the shell in ways no one completely expected. When the ultraviolet spectrographs came online, the quiet shape around Atlast suddenly grew a second ghostly presence. Around 3, Atlast Maven recorded a vast halo of hydrogen, stretching far beyond the smooth cocoon Hubble had revealed. In standard comet physics, such a hydrogen shroud points to water molecules being broken apart by sunlight, hydrogen drifting away as a faint cloud. For Atlast, that process seemed to be happening far more intensely, and at a distance from the Sun where the equations should have been kinder. Modelers began to feed the numbers from Atlast into their codes, expecting to nudge a few parameters and recover familiar behaviour. Instead, every attempt to tame Atlast with ordinary sublimation curves returned something slightly wrong, as though the visitor were running a slow fever from within. One set of hypotheses tried to keep Atlast entirely in the realm of the familiar by postulating enormous stores of buried ice. In that picture, 3I Atlast carried so much frozen water and volatile material that even modest sunlight could drive a giant halo. Another family of models imagined Atlast as a kind of insulated ember, with layers of dust and organics trapping heat over eons. In that scenario, Atlast would arrive already primed, releasing energy in carefully delayed size rather than in one short outburst. A more speculative line asked whether tidal stresses, radioactive decay, or some unknown phase change could be stirring Atlast from the inside. That possibility did not require machinery, only a willingness to admit that interstellar chemistry might cook stranger interiors than the solar system has shown. As teams cycled through these options, the halo around Atlast refused to shrink back into a simple footnote. The visitor seemed to be telling astronomers that something about its internal balance of heat and ice did not belong on old charts. In late-night conversations, some admitted that Atlast felt less like a frozen stone and more like a slow-breathing reservoir of energy. That quiet suspicion nudged the community toward the next round of observations, searching for other signs that 3I Atlast was behaving more like a controlled system than a passive fragment. The next set of images did not come from a telescope built to study comets, but from a mission designed to watch the solar wind. Punch traced the delicate glow around 3I Atlast and drew a line that made dynamicists sit forward in their chairs. Instead of streaming straight away from the Sun, the main flow of material from Atlast appeared to lie almost sideways, hugging the path of the orbit. For scientists who had spent careers teaching that comet tails radiate roughly anti-solar, the geometry around Atlast felt quietly disobedient. When the trajectory team overlaid those frames with tracking data from Psyche's small but persistent nudges, appeared in the path of 3I Atlast. The residuals did not vanish when standard forces were included, and the curve of Atlast refused to relax into a purely gravitational arc. Engineers tried every conservative trick, first assigning the extra push to asymmetric outgassing, or to sunlight catching some hidden facet of Atlast. Each revised model pulled the numbers a little closer, but every time a trace remained, as though Atlast were being guided by a second unseen hand. Non-gravitational acceleration is not a new concept, and veterans pointed to other bodies where jets have steered motion before. Yet the combination of a sideways tail and the measured drift of Atlast made the case feel uncomfortably structured. Around whiteboards, someone eventually wrote a simple question in thick marker: what is providing the extra force on 3I Atlast? No one answered with certainty, but the room stayed quieter than usual, as possibilities were listed and crossed out. For some, the strange tale turned Atlast into a kind of message written in dynamics rather than light. If the halo of 3I Atlast hinted at unusual energy inside the skewed trail, and gentle shove suggested that the visitor was interacting with the Sun in a way models had not anticipated. That realization did not prove anything extraordinary, but it pushed observers to look even more closely at what Atlast was made of, hoping that chemistry might explain why the path of the interstellar guest refused to behave. When the first infrared spectra from James Webb came in, 3I Atlast stopped being just a pretty cocoon and became a puzzle written in numbers. Across the familiar forest of absorption lines, Atlast carried the fingerprints of water-carbon compounds and gases astronomers expected, but the strengths and ratios refused to line up with any standard comet template. In visible light, Atlast already looked oddly muted, the outer shell swallowing more starlight than a normal dusty coma should. In the infrared, the same shell around ThreeI Atlast glowed with a controlled, steady warmth, as if energy were being absorbed and re-emitted through a layer that preferred heat over colour. Teams overlaid the spectrum of Atlast on libraries of solar system objects, from icy nuclei to dark asteroids, and the match always slipped at the edges. Either Atlast carried mixtures of ices and organics cooked in an interstellar environment, far harsher than local comets, or some unknown processing had turned the surface into a material that behaved almost like a natural stealth coating. One group argued that ThreeI Atlast might simply be the first clear sample of long-lived interstellar crust, baked and irradiated until only the strangest grains survived. Another quietly noted that the spectral slope of Atlast dark in the optical and efficient in the infrared resembled the way engineered surfaces are designed when concealment matters more than reflection. No one in the official summaries used the word designed, yet late at night the phrase invisible skin slipped into conversation whenever Atlast appeared on the screen. The more observers tried to corner ThreeI Atlast with familiar categories, the more the visitor seemed to turn sideways, hinting that the outer layer was controlling how much of the interior could be seen. For dynamicists and spectroscopists alike, the message from Atlast was the same. Chemistry alone would not be enough to explain the visitor. They would have to watch how ThreeI Atlast behaved from other angles, measuring how the brightness and pattern of the shell changed, as new spacecraft like Lucy and Stereo caught the interstellar guest from different lines of sight. When Lucy caught up with the interstellar visitor, the curves of brightness held steady in a way that surprised the team. From a distant vantage, Lucy watched Atlast for many rotations, tracing the rise and fall of reflected sunlight. For an ordinary nucleus, astronomers expect a gentle flicker as rough terrain turns in and out of view. In the case of ThreeI Atlast, the light curve looked almost eerily flat, as though the surface remained the same no matter which side faced the spacecraft. Further out, the twin Stereo observatories added their own perspective, watching Atlast from yet another angle around the Sun. Their frames revealed faint streaks of material flowing away in nearly parallel bands, arranged like delicate rails in the haze around the visitor. Simulations showed that random outbursts should have carved irregular fans, but Atlast carried lines that seemed too straight for chance. Some modelers suggested that a nearly uniform crust could smooth away contrasts, leaving Atlast with a face that looked the same from every side. Others proposed that only certain regions on ThreeI Atlast were active launching jets from fixed latitudes that kept the stripes aligned. For scientists used to noisy, uneven comets, the calm behaviour of Atlast felt almost like a refusal to share more detail. The more the numbers insisted on uniformity, the more observers sensed a quiet stubbornness in the way the visitor chose to appear. No one claimed that a smooth light curve proved engineering, yet the combination of steady brightness and ordered streaks turned Atlast into a patient riddle. If the shell were simply the endpoint of long interstellar weathering, then Atlast might be showing how nature polishes some travellers into uniform stones. If something deeper were controlling which patches of the surface could breathe gas, then ThreeI Atlast might be managing its own interaction with sunlight. In quiet monitoring rooms, scientists watched the flat curves crawl across screens and felt Atlast growing more distant and self-contained with each passing hour. By the time every viewpoint had been layered into a single composite, the visitor no longer resembled a familiar type, and Atlast instead demanded to be treated as a whole mystery. That need to step back and see every angle at once led researchers toward a different kind of picture, one where each instrument touched only a piece of Atlast. The next step would be to admit how partial each measurement really was, and to think of ThreeI Atlast the way a story once described many hands reaching for a single unseen animal. When all 15 spacecraft data streams were finally synchronized, the composite image of ThreeI Atlast resembled a riddle sculpted from light. Each probe, from Hubble's crystal precision to Lucy's long-distance glint, had touched only one face of the visitor, yet the fragments combined into something quietly coherent. From one angle, Atlast looked like a shimmering droplet wrapped in symmetry, from another like a cloaked ember glowing through its own haze. When mapped together, the portraits contradicted each other but never fully disagreed, as if each truth about Atlast required the others to exist. A researcher compared it to the ancient parable of the blind explorers and the elephant. Every observer felt a different texture, none could see the whole. ThreeI Atlast had become the same cosmic allegory, a vast shape that instruments could only interpret in pieces. In the synthesis panel, silence replaced debate. The numbers spoke of harmony hidden within contradictions of physics, bending to accommodate something that should not coexist with itself. For the scientific community that was the deeper revelation, Atlast was not defying reality. It was expanding the definition of what reality allowed. The interstellar wanderer passing briefly through the solar system had left behind a mirror, one that reflected the limits of human understanding as clearly as it reflected sunlight. In the end, the official language around ThreeI Atlast settled into a careful compromise. Reports described Atlast as an interstellar relic, shaped by natural processes that humans do not yet fully understand, a phrase chosen to be honest without pretending to know more than the data allowed. Behind closed doors, many teams agreed that Atlast did not need to be artificial to be profound. If ThreeI Atlast recorded chemistry and physics from a star long gone, then the visitor already carried a history no laboratory on Earth could reproduce. Mission summaries emphasized that no unambiguous signs of technology had been found around Atlast. At the same time, those summaries admitted that the range of natural behavior had expanded because of what Atlast had shown. For communicators like Michio Kaku, the message was simple and humbling. 3. Atlast had arrived, behaved in ways that stretched existing models, and left before the community could finish arguing about what the visitor truly was. In late presentations, one quiet line began to appear at the end of slides. The line noted that Atlast remained best described as a natural object, while also reminding audiences that nature as revealed by ThreeI Atlast was clearly not finished surprising anyone. As ThreeI Atlast approached perihelion, telescopes began to record something that defied the ordinary grammar of comets. Instead of reddening under the sun's heat, Atlas shifted toward a sharp metallic blue, a hue that implied ionized gases or a deeper internal energy source rather than passive reflection. Photometric data showed the brightness doubling in less than a day, a flare so abrupt that several observatories rechecked their calibration before admitting the numbers were real. Michio Kaku described it later as a body waking up. If ThreeI Atlast truly generated its own warmth, that would mean hidden mechanisms, radioactive decay, trapped chemical energy, or even internal conductivity converting solar particles into heat. But none of those explanations fit perfectly with Atlast's measured size or its limited exposure time near the sun. Astronomers considered that volatile ices buried under a dense crust might suddenly sublimate once a thermal threshold was crossed, releasing heat pockets that illuminated the shell from within. Others wondered whether microimpacts or piezoelectric stress inside the crystalline structure could mimic controlled heating. Each hypothesis raised new contradictions. The energy appeared too sustained, the colour too consistent, the timing too deliberate. A Thai observer, Wabunla, watching through a backyard telescope, wrote simply, "It feels alive." The phrase spread quietly through astronomy forums, not as proof, but as metaphor, the sense that Atlast was reacting, not merely responding to sunlight. The official communique spoke instead of an internal thermal anomaly. For those who followed Atlast's trail night after night, however, the change in hue marked more than temperature. It marked the moment when ThreeI Atlast seemed to cross an invisible boundary between being observed and observing back, as if the interstellar traveller had begun to reveal its own rhythm, independent of the stars that lit its path. When the non-gravitational acceleration numbers were first shared privately, Avi Loeb studied them in silence. The pattern did not look like random jets to him. It looked like a controlled push acting on ThreeI Atlast. Across weeks of calculations, Loeb kept returning to the same conclusion, that the extra force on Atlast followed a geometry too clean for chance. Where others saw a statistical nuisance, he saw an invitation to at least entertain the idea of a techno-signature linked to ThreeI Atlast. Loeb's papers did not declare Atlast a probe, but they insisted that technology be included among the hypotheses rather than quietly discarded. He argued that if sunlight reflecting off a thin surface or exhaust from engineered vents could reproduce the acceleration curve, then ThreeI Atlast might be acting less like debris and more like a device. Colleagues reminded him that outgassing and irregular shapes can also mimic thrust, and they urged patience before elevating Atlast to anything exceptional. Loeb answered by asking for more data, requesting raw tracking logs, thermal maps, and any high-resolution frames that captured ThreeI Atlast near perihelion. To him, withholding possibilities because they were uncomfortable was less scientific than testing them and letting Atlast itself rule them out. In public talks, he softened the language, calling ThreeI Atlast a natural object with room for surprise, but the subtext remained clear. If numbers continued to favour a structured, repeatable push, then ignoring the technological reading of Atlast would become harder to justify. That tension between caution and curiosity set the stage for a quiet controversy when key images of ThreeI Atlast failed to appear where everyone expected them. The first hint of trouble came when researchers went looking for the sharpest views of ThreeI Atlast from Mars Reconnaissance Orbiter and found only gaps. Tracking logs showed that MRO and its high-rise camera had enjoyed an almost perfect viewing geometry, yet the public archive held no close frames of Atlast at the expected times. Official explanations pointed to routine complications, to calibration sequences, pipeline delays, and even the timing of a government shutdown that slowed uploads. On paper, every reason sounded mundane, but the coincidence between missing imagery and the most dynamic phase of ThreeI Atlast's passage made people uneasy. In internal briefings, space weather specialists highlighted flow patterns around Atlast that seemed to bend sunward rather than away. One veteran quietly described the configuration as reminiscent of a spacecraft performing a braking burn, an analogy that clung to ThreeI Atlast long after the meeting ended. No formal report accused any agency of hiding evidence, and most scientists stressed how easy it is for data to fall through cracks when missions juggle priorities. Even so, the absence of high-resolution views at precisely the moment ThreeI Atlast flared and changed speed became another anomaly pinned to the visitor's name. For cautious observers, the gap in the record was simply one more variable to track. For those already wondering whether ThreeI Atlast might be managing its own motion, the silence in the image archive felt like part of the story, and pushed attention toward the deeper question of how the interstellar traveller's path had been drawn in the first place. Orbital analysts noticed another quiet peculiarity when they plotted the path of ThreeI Atlast across the solar system. Instead of slicing through at a steep arbitrary angle, Atlast slipped almost perfectly along the plane, where the major planets orbit as though following a pre-drawn highway. Statistically, an interstellar body can arrive on any inclination, and many do, but the alignment of ThreeI Atlast with the ecliptic sat in the thin tail of probability curves. Some teams treated the match as coincidence, adding Atlast to a growing list of rare but natural visitors. Others, including voices like Michio Kaku, asked a different question. If a distant civilization ever wanted to survey a planetary system efficiently, would it not send its scouts along the shared plane of those worlds just as Atlast had done? That thought experiment did not prove intent yet. It reframed the way ThreeI Atlast was discussed in quiet seminars. Suddenly, the orbit of Atlast became more than a set of numbers. It became a hypothetical choice. Engineers ran counterfactuals asking how much delta their craft would save by copying the gentle entry that ThreeI Atlast had taken. The savings were real, and the idea of deliberate navigation clung to the whiteboard long after equations were erased. In public, the wording stayed careful, speaking of a trajectory consistent with low inclination approach. In private, some admitted that ThreeI Atlast behaved as though it had found the system's natural shipping lane and settled into it. Whether that lane was chosen by chance or by design remained unsolved. But the graceful way Atlast threaded through the planets ensured that any discussion of purposeful navigation would have to keep returning to the interstellar traveller's quiet, almost courteous path. When radar dishes at Goldstone turned toward the passing interstellar visitor, the echoes came back with an unexpected texture. Instead of the soft, featureless murmur expected from a rounded icy body, the returning signal from ThreeI Atlast rose and fell in jagged steps. Signal analysts described the pattern from Atlast as structured noise, a phrase usually reserved for reflections off surfaces broken into panels or facets. Simulations using smooth nuclei could not reproduce the sharp transitions, so teams began to feed in models where ThreeI Atlast carried ridges, seams, or repeating blocks. In those experiments, only heavily segmented shells produced echoes resembling what Goldstone heard from Atlast. The match did not prove machining, but it pushed some researchers to compare the visitor's radar fingerprint with that of industrial debris in Earth orbit. Spectroscopists added their own piece, noting that the ionized metals traced around ThreeI Atlast did not fit the usual cometry proportions. One cautious memo suggested that an unusual concentration of processed-like material might be clinging to the outer layers of Atlast, whether by natural sorting or some more elaborate history. Official summaries spoke instead of a highly heterogeneous surface, keeping ThreeI Atlast within the language of geology. In late-night discussions, however, the image that clung to minds was simpler. A picture of Atlast as a traveller wrapped in overlapping plates, each one catching and returning radar pulses like the skin of a distant, forgotten machine. As tracking continued past perihelion, analysts noticed that the extra push on ThreeI Atlast was not constant. Instead, the non-gravitational acceleration around Atlast rose and fell in a slow, repeating rhythm. Random jets should have smeared the signal into noise, yet Atlast traced a curve with gentle peaks and valleys. Plot after plot showed the same oscillation, as if some internal system on ThreeI Atlast were quietly adjusting itself. Dynamicists proposed that active patches on Atlast might switch on and off as sunlight swept across the shell. Thermal modelers suggested buried reservoirs could vent in cycles pumping and relaxing as ThreeI Atlast rotated and cooled. But the regularity bothered people because the timing around Atlast looked more like a scheduled check than a spasm. In one seminar, Michio Kaku compared the curve to a thermostat, hinting that ThreeI Atlast might be tuning its own environment. Infrared observers added that a hotspot on Atlast seemed to brighten and fade in step with the dynamical swings. The coincidence did not prove machinery, yet it kept pushing the phase system adjustment into discussions of ThreeI Atlast. To stay cautious, teams logged the effect as a periodic non-gravitational term while quietly admitting that Atlast behaved uncannily, like a system learning to keep itself in balance. The first real jolt came when the Deep Space Network briefly lost contact with the transponders tracking ThreeI Atlast. For a few tense minutes, the usual stream of timing tones and position updates from Atlast went quiet across the consoles. When the data link returned, trajectory fits showed that ThreeI Atlast no longer followed the shallow groove of the ecliptic. Somewhere inside that blackout, Atlast had tipped away from the planetary plane, as though stepping off a well-worn path. Engineers hunted for mundane causes, checking for clock errors, software resets, or mistagged observations tied to ThreeI Atlast. Nothing obvious emerged, and the revised orbit of Atlast stubbornly preserved the same sideways tilt. In meetings, the change was described as an unexpected out-of-plane component, careful words that hid the unease. For those who had already watched the slow, rhythmic thrusts from ThreeI Atlast, the new vector looked like more than drift. Michio Kaku asked aloud what no one wanted to write in a memo, whether ThreeI Atlast had just chosen to leave the crowded sheet where most of the system's hardware lived. The idea sounded dramatic, yet the numbers showed a clean, deliberate-looking slide. Officially, the maneuver remained a quirk of non-gravitational forces acting on ThreeI Atlast. Unofficially, many felt that the interstellar traveller had turned its head, and that whatever came next would decide whether Atlast had simply reacted to sunlight or quietly responded to being watched. On the night when James Webb finally locked its gaze onto ThreeI Atlast control rooms around the world grew unusually quiet. For several long hours, the telescope tracked Atlast across the sky, collecting a continuous stream of infrared light from the departing visitor. When the first thermal maps were reconstructed, they showed ThreeI Atlast not as a smooth ember, but as a patchwork of hot and cool regions arranged in a surprisingly ordered way. Instead of random hotspots, Atlast displayed repeating zones as if heat was seeping through a pattern of hidden ribs or panels. Spectral energy distributions from ThreeI Atlast hinted at complex molecules and possible metallic components layered over the expected ices and dust. Engineers remarked that the temperature gradients around Atlast looked less like a melting snowball and more like a system bleeding off residual power. In the days that followed, observers watched ThreeI Atlast dim in the infrared faster than models predicted, even as the non-gravitational acceleration increased. It was as though Atlast were methodically shutting down its warmth while giving itself a final efficient push onto an outbound path. Official reports called the escape of ThreeI Atlast an effective utilization of solar system dynamics, avoiding any talk of intent. In late seminars, however, some quietly wondered if Atlast had simply finished whatever survey it came to make, and then chosen the cleanest line back into the dark, leaving only cooling numbers and a vanishing streak of light behind. While ThreeI Atlast slips back into deep space, astronomers turn to another quiet mystery the world called K2-18b. K2-18b circles a dim red star inside its so-called habitable zone, the band where starlight could allow liquid water on a surface. Unlike Earth, K2-18b is a mini Neptune several times more massive with a thick envelope of gas that wraps the planet like a deep blanket. Observations with James Webb have found hints of water vapour in that blanket, suggesting that under the haze, K2-18b may hide vast layers of cloud or even an ocean. Climate modellers run two competing stories for K2-18b, trying to understand whether the planet is gentle or hostile. In one set of simulations, the greenhouse effect on K2-18b is moderate, and heat spreads just enough to keep a global ocean in a stable twilight warmth. In the other, the atmosphere of K2-18b traps energy like a runaway Venus, and any ancient sea has long since boiled away into a thick, crushing fog. Both stories fit pieces of the spectrum, and ThreeI Atlas becomes a distant reference point, reminding scientists that data can support more than one reality at once. The ambiguity forces researchers to leave room for both a living ocean and a dead shroud when they speak about K2-18b. For listeners drifting towards sleep, K2-18b is less a resolved world than a place where waves might roll forever in darkness, or where rock lies bare beneath endless clouds. That open choice mirrors the way ThreeI Atlast lingers in the mind, both natural and possibly more depending on which model you let guide your imagination. From K2-18b, the narrative will soon slide back toward closer shores to Mars and its slopes, where the search for liquid water becomes more than a thought experiment. The real jolt for K2-18b came when James Webb picked out dimethyl sulfide in the planet's infrared spectrum, a molecule on Earth mostly made by living oceans. Suddenly, K2-18b stopped being just a climate puzzle and became a potential home for a signature that, if confirmed, would be the first clear hint of biology beyond our sky. For scientists still weighing the mysteries of ThreeI Atlast, the appearance of DMS on K2-18b felt like a second whisper from the universe. On Earth, plankton and other marine life breathed dimethyl sulfide into the air above the seas, so seeing the same chemical on a distant world pulled human intuition strongly toward life. Chemists, however, cautioned that exotic reactions in a hydrogen-rich atmosphere could also assemble DMS without a single cell ever forming. In hushed workshops, they built long chains of reactions trying to show how K2-18b might mimic life the way Atlas seems to mimic intention in its measured drift. The result was another fork in the road, one branch pointing to alien microbes stirring beneath perpetual clouds, the other to strange but lifeless chemistry. Telescopes like the coming Extremely Large Telescope may one day separate those paths, just as future missions might re-examine ThreeI Atlast and refine its story. Until then, DMS remains a question mark hanging over K2-18b, a spectral smudge that refuses to choose between biology and geology. In the soft logic of the night, the molecule and Atlast belong to the same family of hints, reminders that the cosmos can speak in half-finished sentences and leave the endings for human minds to supply. Long before anyone worried about ThreeI Atlast, Mars had already been whispering about water in its own delicate way. On steep crater rims, dark streaks appear with the warmth of Martian summer and then fade again as if the planet is breathing in slow motion. Researchers think these lines may be the marks of salty water, thin brines that trickle down the slopes before freezing or evaporating away. For scientists who now watch Atlast and K2-18b for hints of habitability, those Martian stains feel like closer, more tangible cousins. Pure water would seize up quickly in the chill of Mars, but mixed with perchlorate salts, it can stay liquid at far lower temperatures. In laboratories on Earth, microbes have been found thriving in similar brines clinging to life, where most chemistry slows to a crawl, the way ThreeI Atlast clings to the edge of existing models. That parallel comforts some researchers because it suggests that life does not always need gentle oceans. Sometimes a thin seasonal trickle is enough. If Mars ever raised its own microscopic civilizations, their last refugees might be in these salty threads hiding from radiation in the cracks of rock, while missions chase at last far beyond. As you drift towards sleep, you can imagine those brines gliding silently down red slopes, leaving only faint marks that robots will one day follow. From those quiet Martian gullies, the story will slide next into deeper shelter, into caves and lava tubes where the search for past life becomes a journey further underground, just as thoughts of Atlast sink further into the dark between stars. On the flanks of ancient volcanoes, Mars opens dark mouths into the rock caves and lava tubes where sunlight never reaches. Planetary geologists imagine these hollows as natural bunkers, places where past Martian air and warmth might have lingered long after the surface froze, while ThreeI Atlast glides far above in another story. Inside such tubes, stone and dust would shield any chemistry from the harsh rain of cosmic rays. If microbial life ever took hold on Mars, many astrobiologists, including voices like Michio Kaku, suspect its last strongholds would be in these buried corridors, just as Atlast seems to hide its own secrets behind a controlled shell. Robotic scouts have already mapped Skylight's raw windows in the crust that drop into blackness. Engineers sketch small, careful machines that could descend those vertical shafts, watching their own cables pay out, while the memory of ThreeI Atlast reminds them how easily a world can keep its mysteries at a distance. In the quiet of those imagined Martian tunnels, ice might cling to ceilings and walls, preserving fossils or frozen chemistry from a wetter age. The silence in those tubes feels similar to the silence between the stars, a kind of waiting space where Atlast once passed, and left only faint signals behind. As you picture those caverns cool and sheltered, you can feel the story folding inward from open slopes to hidden chambers. From that darkness under Martian volcanoes, the path of thought will soon rise back into the sky, toward flashes of lightning that reach upward, and to the strange high clouds where Earth's own atmosphere reveals phenomena as surprising as anything ThreeI Atlast has shown. High above the storms of Earth, in a layer of air thinner than any desert lightning sometimes moves in the wrong direction. Astronauts on the station have watched ghostly red tendrils burst upward toward space, and the sight unnerves them in the same quiet way that ThreeI Atlast unsettles dynamicists. These flashes are called sprites, and blue jets, eruptions of plasma in the mesosphere that bloom for milliseconds then vanish. In textbooks, lightning is supposed to stab downward, but sprites and jets ignore that rule just as Atlast ignores simple gravitational paths. Cameras on the station have caught entire forests of these upside-down bolts, delicate structures branching and fading like bioluminescent coral. Analysts tracking the events admit that the statistics are thin and the physics incomplete, leaving Earth's own sky as puzzling as the shell of Atlast. To catch more of these rare glows, agencies invite pilots, skywatchers and amateurs to report what they see from the ground. The network of human eyes and small cameras echoes the many spacecraft turned toward ThreeI Atlast, each observer holding only one piece of a larger pattern. For some sprites make the atmosphere feel less like a settled dome, and more like a restless ocean of charged mist. In that restless sea, Atlas becomes a distant cousin, another reminder that familiar environments can harbour behaviour no one fully mapped in advance. From these silent bursts over thunderstorms, the narrative will slide naturally into other human-made lights in the sky, toward the strange artificial stars that astronomers create when they try to tame the blur between Earth and the distant paths of Atlast. Far above the tallest clouds, a faint haze of sodium atoms floats like invisible dust around the planet. When powerful lasers climb into that layer and make the atoms glow, astronomers create artificial stars to sharpen their view of worlds and of travellers like ThreeI Atlast. From the ground, telescopes watch these human-made points shimmer, then use the distortion to untangle the blur of Earth's air. With that correction in place, distant galaxies resolve exoplanets emerge from glare, and the path of ThreeI Atlast can be tracked with finer care. The sodium itself likely began as cosmic dust, tiny grains shed from comets, and meteor streams long before anyone noticed Atlast. In the upper atmosphere, those grains break apart, seeding the thin layer that now answers the call of laser light, and quietly serves the study of ThreeI Atlast. There is an odd symmetry in using starlight and stardust to steady our gaze on an interstellar guest. The same universe that shaped ThreeI Atlast also sprinkled the ingredients that let human optics reach up and meet the visitor halfway. For many researchers, that loop feels almost emotional, a reminder that observers and observed are built from the same scattered elements. When the artificial stars wink on and off above observatories, they seem to echo the brief appearance of three. Atlast itself, a manufactured clarity chasing a natural mystery. From those man-made beacons, the story gently widens again toward rocks that fall from other worlds, and to the rare meteorites that may carry the signatures of a scorched planet, as distant in its own way as the cold track of Atlast. The story of rare meteorites from Mercury begins much closer to the Sun than the path of ThreeI Atlast. Two unusual rocks found in Africa carry a chemistry that looks like the stripped crust of Mercury, with far less iron than typical meteorites. For decades, dynamicists argued that fragments from Mercury should almost never reach Earth. The planet sits deep in the Sun's gravity well, and any debris must first fight its way outward, a journey that sounds as improbable as the interstellar dive taken by Atlast. Recent impact simulations change that picture. They show that violent collisions can hurl shards of Mercury onto elongated orbits, where gentle tugs from Venus and Earth slowly reshape their paths, the way repeated passes around the Sun shape the track of ThreeI Atlast. In those models, a small fraction of fragments eventually cross Earth's orbit and fall as meteorites carrying a memory of extreme heat and tidal stress. If the African stones truly came from Mercury, they prove that even worlds close to the Sun can send messengers across space, just as Atlast arrived from the dark between stars. The joint Bepi-Colombo mission will test this idea when it finally circles Mercury and samples the real crust. Comparisons between its measurements and the meteorites could confirm a journey as unlikely in its own way as the passage of ThreeI Atlast. Holding such a rock would be like holding a chipped scale from a scorched planet, a small solid echo of forces that carved whole orbits. In that sense, the Mercury fragments and ThreeI Atlast belong to the same family of travellers, each one rewriting what once seemed impossible for gravity to arrange. From a distance, the different mysteries begin to look less like separate stories, and more like threads in one fabric. K2-18b, with its possible ocean, the salty slopes and caves of Mars, Mercury's wandering fragments, and the strange flashes in Earth's sky all weave around the path of ThreeI Atlast. Each clue stands alone, but together they form a pattern in which the universe keeps hinting at complexity just beyond current models. ThreeI Atlast is only one strand in that pattern, yet at last has become the emblem of how quickly certainty can unravel. Spectra that refuse easy labels, orbits that suggest choices, chemistry that looks almost alive, all of them lean toward questions rather than answers. In that sense, Atlast and K2-18b and the Martian brines are not solutions, they are carefully placed invitations. Michio Kaku sees in these invitations a cosmos that is talking softly through numbers and faint lines of light. Avi Loeb sees in ThreeI Atlast a reminder that ruling out bold possibilities too soon is its own kind of blindness. For anyone listening, the message is that nature is willing to play on every scale, from tiny microbes to interstellar travellers like Atlast. Whether the tapestry one day reveals other minds or only wilder physics depends on how honestly humans follow the threads left by ThreeI Atlast. As the interstellar traveller fades into the dark, the questions remain bright, stitched into the sky above every sleeping world.